I don't know what happened yesterday at 5, but hopefully some people dialed in. One of the bigger issues this morning seemed to be that the homework for StripMap app required or suggested downloading other data sets, but we had not really gone through the downloading process, and there were some questions about how to get how to change those links for the download of ALOS data from different places. So this morning we went over that process a little bit. I don't know if others have had similar questions and whether we should go over that again now. Typically for this hour, we just answer questions about homework, and people who have done the homework have been encouraged to share their results and either just show the result and so we can see what the interferogram looks like, or if they ran into problems in the processing, to articulate that, and then we can figure out what went wrong. The other thing, then there were some INSAR and correlation homeworks as well that were relatively straightforward calculations, but some people had some questions about those also. So we can go over that if you like. At least give you some hints. Does anybody have an example of processing that they would like to share? Some of you students I know are pretty experienced. I recognize some names. So maybe you have done a homework and would like to share it with us.
Hello.
Yes.
I have a question. Last night I tried to run this the strip data. I'm saying the script file, and it worked correctly. But in the morning again, when I just wanted to try that again, I don't know what happened, that it's not working correctly. And it seems that if I run the file over and over, it's not working, and I don't know what's the problem with that.
That's interesting. Did you start from the beginning both times?
Yeah, every time from the beginning, and it says that files exist, but it's not creating the interferograms, or all the figures that I got last night are disappearing at the end of the scripts, and I don't know why. I thought that maybe it's better to just delete all the data from the beginning, from the folders, and just try it again. But I wanted to ask what happened, that what's wrong with that it happens.
So generally speaking, if the data exists, it should not worry. It should just proceed on to the next step. Maybe you can bring up your notebook and show us where it first fails in what you did this morning. Is that possible?
It's in the other PC, so
I see. So it's going to be difficult to, unless we can replicate the problem, it's going to be difficult to know specifically what went wrong.
Yeah, I know.
Yeah. So has anybody else had a similar experience that you ran it twice and the second time it didn't work?
All the figures are disappearing. I don't know why.
Figures are disappearing.
Yeah.
And then here's someone who had the opposite experience. First, it was not working yesterday, and now it's working today. So,
so good for him.
Yeah, it's a random process. Maybe you just need to run it a third time, and it'll suddenly work.
Actually, I tried many times, maybe 4 or 5 times, and I just, okay, maybe it's because I tried that many times. It's better to just delete all the data from the folders and try it again. But before that, I just wanted to ask these questions from you. Maybe you have a better idea.
Yeah, if you run into hiccups, one approach is always you pull up a terminal. It when it downloads data, it creates some subfolders. If you delete those and start from scratch, that's the safest thing probably to do.
But maybe, let's see, I'm just trying to think if I have, does anybody have a ability to share what they did? And then we could maybe go to the terminal on your screen and CD to the directory where the folder where the data are, and we can just sort of look at that folder, see what the structure is, and then you could compare it to what you have in yours. You should have all the same files. That's one way to try to debug this without Masa actually being able to share a screen.
And Masa, there was a good point in chat. When you run the notebook, make sure when you look at the top right corner that the kernel is set to UNAFCO. If you deleted the notebook and pulled it back in, it may have switched back to Python 3. Usually once you saved it, once it auto-saved once, it should be fine.
It was in UNAFCO, but some things happen is that during running the script, I lost my connection to server, and maybe it could be one of the problems.
Yeah, it could be that if you lose the connection long enough, the kernel does break, and you may have to restart the kernel and possibly start from scratch. Depends on how long you were disconnected. It may or may not lose the sort of variables that are stored in memory.
Yeah, my network is unstable sometimes, and yeah, it just everything just disappears and have to start from the beginning.
Yeah, if you break the kernel, the safest thing is to start from the beginning.
But the issue is you should not have to go in and delete all the directories, right? It should just work by, if it finds the data, then it will skip that step. If it doesn't find the data, it will do the step.
Yeah, so one trick that you could try is in the notebook. Does anybody have a notebook up? Let me bring the notebook up.
Sorry, I interrupt you. It should tell me that data exists, but it didn't tell me that it exists.
So it doesn't tell you it exists, and it still skips the step?
Yeah, it skips the steps and go to the next one, and nothing happens.
So I'm not sure if the strip map app notebook changes directories sometime internally. You know, in some notebooks there's like a change of the directory, which means that if you restart the notebook, you're now in a different directory. To make sure that you start from scratch, let me just show you this real quick. One way to make sure that you start from scratch. Not sure if you see my screen. Do you guys see my screen?
Yeah.
You can go to kernel and either do restart or restart and clear output. When you restart the kernel, then everything starts from scratch. So it may be that, you know, as you go through the notebook, you start out in some sort of initial directory. Then internally in the notebook, it switches into a data directory. And so if you just start the notebook again from the beginning, it starts from a different place in the path. That makes sense? So you can either manually type in cd.data to get back to where you started from, or you restart the kernel to wipe all that information and to get you back into your original folder.
Okay.
Yeah, that makes sense. That maybe if it got interrupted midstream, it's in the wrong default directory at the start. Yeah. Okay.
Yeah, so that's also a good way of clearing all the crap that's in memory and make sure that you're starting from the beginning.
Yep. Okay, that's a good suggestion.
Thank you.
So Riley has a basic question on strip map. Do some satellites collect data in both strip map format and TOPS? So there's only 2 satellites, to my knowledge, that are sort of operationally using TOPS mode. That is Sentinel-1 and the SAOCOM system that the Argentinians are running it through CONAI. Both of those systems can do strip map processing, and in some cases, Sentinel, I think in certain areas of the world, does do some sort of strip map processing, but it's not prevalent for Sentinel anymore. I think they tested it a lot more earlier on. Franz may know more, since he manages the archive up there at ASF, how much strip map data is currently being processed.
Yeah, there's not a ton of strip map data from Sentinel-1, but in theory, it has both of those modes. So often in very specific places, you may run into a strip map data set. I think SAOCOM, I think the SAOCOM TOPS mode is not INSAR enabled. Is that true?
I think that's right. I've heard that. Yeah.
So
Yeah.
for the interferometric acquisitions of SAOCOM, it most likely is strip map.
Yeah, right. Which areas are collected in strip? Oh, for Sentinel, you mean?
I can find out during the next 10 minutes. I think it's mostly a resolution thing. There's some places where people wanted to have a little bit higher resolution, and the strip map, I think, is a little bit higher resolution than the TOPS.
So I have a suggestion, Franz. Maybe a good thing to do right now, which would kill 2 birds with 1 stone, as we say, would be to bring up Vertex, go to select an area where you might expect to see strip map, and then show people how to search for strip map data in the Sentinel archive. Because that was one of the issues that we faced in the morning. We did muddle, Haresh and I did muddle through it, but I'm not an expert at Vertex. We did find some scenes over Vietnam for Lien. So I imagine if you just selected all of Europe, big box around Europe, and then filtered on strip map. Oh, I can't hear you if you're talking, Franz.
I'm guessing strip maps mostly acquired over islands.
Sorry, I was talking.
Yeah,
myself.
start again. We didn't hear anything you said.
So if you go to start Vertex, you will go to search.asf.alaska.edu, which I've told myself now twice. And so the default search is a geographic search, which means that you search via either shapefile or a bounding box. And it also defaults to Sentinel-1. When you have this, the one thing you can do, you can just set a filter and filter for certain beam modes. So you see here in the filter window, you can drag and drop a geospatial extent, like a JSON file or shapefile. You can set start and end dates. You can filter by file type, which is GRD or SOC mostly. GRD is the ground range detected format, which has the phase removed. And the SOC, the singular complex dataset, is the dataset that has the phase in it. So if you want to do interferometry, you want SOCs. And then you can search by beam mode. And in the beam mode, it has the two dominant beam modes that Sentinel-1 is collecting is the so-called IW modes. That's the interferometric white swath mode, which is collected in a TOPS mode, acquisition mode. The EW, the extended white swath mode, is also a TOPS acquisition mode. Those two are a little bit different. The EW has a larger swath and a little bit lower resolution. This one is, I think, collected mostly over sea ice and over the oceans and near sort of the Arctic coasts. The IW mode is the dominant mode for all the inland land masses. In addition to the IW, there are a few modes that are labeled S. These are the regular strip map modes, and there are different kinds of strip map geometries. So you can just filter by those to see if you find SLCs. And there's 11,000 SLC related files. So if I just
That's
find
over the globe or
globally.
globally, yeah.
So I'm just going to look for the 5,000 top files and search for those. And it should give me their footprints once the search is done. Still looking.
So there are 3 subswaths of the TOPS mode, but there are 6 different beams for strip map. Do you know if those are 6 different look angle ranges, or are they overlapping in some way? Do you have any idea?
I don't know for sure, but I think it's different look angle ranges. Oh, here we go. So here's the, here are the locations. Do you see this?
Yep. So Gareth was right. There's a lot of islands, but there's also quite a bit over land.
Some Galapagos. There's some place in, I think, around Houston, maybe, right? But some modes are at a high resolution mode. At the sort of strip map high resolution mode. There's some in Holland. So there's some of these locations. So they're few enough so that you can find most of them with a global search. So in this case, it found, about 5,000 scenes of strip map data spread out fairly randomly globally.
So while you're there, maybe you could demonstrate how to get that link that would be put into the strip map app for ALOS. Well, I guess now you're doing Sentinel, but maybe it's the same thing. By copying the URL of the data set.
Oh, yes. Copy scene name.
No, normally what you do is you put something in your cart.
Right.
Like pick a scene and stick it in the cart, and then on the right, under the downloads thing, there's a copy URL.
Okay. So, so here you have your scene list. These are all the 5,000 scenes you found. If you wanted to pick a specific one, say I like this particular scene, once you click on it, it highlights it on a map. So I found a Houston scene in this case. So it's the one with the red frame. And let's say that I like this scene. I can put that in cart. There's a little cart symbol in that interface. As you can either put it on cart here. There's also a cart symbol over here. Either one of those works. When you click on cart, it added it to my download queue. So it's now in carts. I have 2 files in carts. And so here, when I click on one of those, you say that I get the copy file ID.
So at the bottom, there's a copy URL.
Oh, here's a copy URL. So let me delete this guy. So now I have this SOC here, and here I can copy the URL.
Right, and that puts it in your clipboard, and then you can paste that wherever you want.
So here's that URL. It says, datapool.asf.alaska.edu and so on. It has the full URL to the data set.
Right. So there's a similar kind of URL for the ALOS data that you would use for StripMap app, which is acquired by the same method that Franz just demonstrated.
Right, and for ALOS, the main thing you have to do is up here where it selects the data set you're looking for. There's a variety of different data sets that are in the archive. Sentinel-1 is what's set by default. If you click on that list, the next one down is ALOS Pulsar. The ASF archive currently has ALOS Pulsar data over North and South America, plus selected data sets over Greenland and the Antarctic Peninsula. We are actually currently in the process of rolling on the global ALOS-1 archive. So JAXA is rolling its ALOS-1 archives holdings over to ASF and uses ASF services to make that data set globally available. So the global ALOS-1 archive will become available through ASF soon, as soon as the data transfer is completed. But for now, if you look for scenes and data stacks, the best places to look for is sort of North and South America, where we have most of the data. And so, yeah, you can basically draw a bounding box, select ALOS, select some sort of a start and end date, say 26 October 1st to 27 June 12th. Then you can select filters here if you want specific data sets. 1.1 is the SLC data. And then you go and search. In this case, you found 27 files. And then you can pick one that you like, add it to the download queue. And then copy the URL. And the URL looks a little bit different. And so here you have the URL for this ALOS data set.
Great. Are there any questions about how to get the URLs that you need to do StripMap app still? Should be hopefully clear by now. So there's a bunch of questions. I'm not sure if they've been answered. The chat is a little bit difficult. Mohammed's asking about authentication failure. So probably the netrc file is not set up correctly. Have we addressed that?
It could be that, or it could be he hasn't signed the EULAs, which we found with some people yesterday in the evening.
Yeah, sort of to find out if you have the right EULA set. So I always have to Google for it because I don't know for sure. But if you Google for Earth data login NASA, the very first link gets you to this page, urs.earthdata.nasa.gov. There you can log in with your username and password.
Hello.
Yes.
Yeah, I can log in it and I can access my profile. But
Okay.
But while updating, I can update everything like Alaska and other applications. But even after updating, it gives me an error of username password authentication failure.
Okay. So these are the EULAs that you should have signed. There's two ASF EULAs.
Did you do that, Mohammed?
You have those two, the Alaska Facility Data Satellite Facility Data Access and the Alaska Satellite Facility Data Access Egress Control.
I don't know how to check this one. I can share my screen if you want.
That'd be great. Yeah.
And I have to stop sharing. Here it is.
So can you see my screen?
Yes.
Yeah. So if you click on Applications.
Yes.
And Accepted EULAs.
Under applications.
Yeah, it's loading.
Mouse over applications.
No, it's going. There we go. So you have the egress control and the data access. Yeah, you should have all the ones. You need the one that you don't have is the Griffin. Are we working with Griffin data here? No, right? No, not at this stage.
We'll do later.
Yeah, if you go to authorized apps, there is somewhere, where's the Griffin one? I don't see it.
There it is.
Oh, here it is. Griffin prod.
And this one?
Yeah, so authorize the at least the production one. There's an authorize button all the way in there. Yeah. I think that's the one I have.
Well, you're a fast reader.
I'm having this problem since yesterday.
Okay, excellent. I think that should get you there.
So let's go back. Can we go to your notebook environment? And
One thing I would advise right now is just copy and paste the URL for the data into a new browser tab and see if it downloads, because you're logged in and you have all your things set up.
If I click here,
Yeah.
so then it will start downloading a file.
Okay.
In which case, then you have the right permissions.
Yeah.
They're all set up.
maybe the netrc file is not set up properly. Have you checked that?
I did that, but I can show you again. So,
Just
maybe.
note, if you do show us your netrc file, we can't see your password. So afterward, you should probably change your password.
Okay.
ls-a
Yeah.
and go to your home directory actually. So type cd first on its own.
Yeah, sorry. So it's
ls-a will show all the hidden files. Okay, so it's there.
There's your netrc. It's in the right place, and you can do a more or a less or whatever you want on
Cat.
VI or Vim.
Well, you can check it yourself just to make sure that your username and password are properly specified for the Earth data. And you can log in, so your password works. So we know that.
Yes, you
So
have data access. It's probably the formatting. Make sure that the netrc is in 2 different lines. The username and password is in 2 different lines.
yeah,
it was in, I guess, in work folder.
Oh,
No, type cat and .netrc, and that will show us your password, just so you know. But it will see whether you have a terminal readable file.
so and dot.
I was using VI, so.
Oh
Okay.
yeah, that's fine.
It's fine too.
Hey, like you already.
I think I have.
Oh, yeah. Do just VI and then dot periods.
Because I'm using some other ones, so a keyboard is changed automatically sometimes.
Oh yeah, you haven't actually added where it says username. You have to put your username in, and where it says pass, you have to put your password in. And you don't have to do that while you share screen, but that's the issue.
Okay.
that's the issue.
Okay. So you I have to put my name that is in Earth data login and the same password.
Yep.
Correct.
Password, right?
Okay. Okay. So thank you very much.
All right, going back to the chat. Where was it? There were some other questions, I thought.
Oh, on the egress, Emma, I'm not sure if you need it. If it probably doesn't hurt to activate it.
Okay, thanks.
ASM
Just wanted to
data
check.
access egress control. I don't know if you actually need it for this particular class.
Okay, thanks.
So with this question about Sentinel-1 not covering Canada get answered? It does cover Canada, just not in strip mode.
Yes.
It's not doing it in strip mode because most things are done in this IW interferometric wide swath mode.
Really, we didn't even check what dates most of those were, but I bet they were all in like 2014 and 2015.
That's right. They were mostly doing that as sort of initially. Question about the ionosphere scintillations. I think this will get answered in the afternoon session on ionosphere. We'll see examples of what ionosphere looks like. At some level, you kind of have to know what you're looking for, or you could go to an ionospheric database that tracks activity over time. But I think you'll see the examples this afternoon, and we can address that better later. Is ASF considering including ALOS2 data? I think that was answered, right?
So for ALOS2, so we'll have the full global ALOS1 data. For ALOS2, we will be hosting some ALOS2 data, and that's the ALOS2 ScanSAR data. The SOCs are still limited to PI access, but the ScanSAR data will be made free and open, and ASF will host them.
But the ScanSAR data is generally interferable. ISCE2 at the moment, I don't know if the public release has the ALOS2 ScanSAR processor in it, but I know there's a version that is either done or almost done that can do the interferometric wide swath ScanSAR processing for ALOS2. So that should become available sometime.
Are they burst synchronized enough so that it generally works, or is it more luck?
I think it's almost always working, from my understanding. Yeah.
The StripLab app notebook refine co-registration are estimated using incoherent cross correlation and rubber sheeting. Also uses incoherent cross correlation. May I ask if there is a difference? The basic approach for the refine co-registration step and the step to do ionospheric correction is the same. In both cases, it uses incoherent cross correlation to find offsets between images. The difference is that in the refine co-registration, we're looking for only sort of a constant shift in X and Y between the two images. For the rubber sheeting, we usually are calculating a denser grid of offsets to be able, because the ionosphere in some cases, when there is scintillation, it causes a distortion of the image where the offsets are not constant throughout the scene. They may be much larger in a fairly narrow part of the image and much smaller in other parts of the image. So we are calculating a denser grid of offsets and then use that to sort of pull the two images together. But in concept, it's the same approach.
Okay, I'm working back a little bit. So Mohammed asked, I have a question about homework in notebook 1.2. What was that question?
Yes, so I was just working. Wait, can I share my screen?
Sure.
Cool. So yeah, so I've been working at question number 5 for the homework assignment, and then I was using we would have to look for different depths to search for the parameters, and I was using a depth of in the range of, and then I was using the volume that was, can I zoom in? Yeah. So, but I have an issue, like whatever ranges I run, also have some problems like the depth is calculated at 2.52 kilometers, and the volume is then calculated at 0.0032 kilometers. I did it again, just increase the ranges, but still like.
But your depth range is less than a kilometer. It's about 1/10 of a kilometer, right? It's exactly 1/10 of a kilometer. So you're only going to find stuff in that range. Don't you want the wider range to search?
Yeah, like I can do that. Maybe from to 7 to.
Well, so what was the optimal solution before? What was it set to originally? 2.5?
So originally, it was 2.58, if I'm not wrong. Yeah.
Well, if I were you, I would live dangerously and pick a really big range and see what happens.
Okay. Cool.
But I don't know, Franz, it's your notebook. So what would you suggest?
So maybe I would just start from 2.4 to 2.8.
I'd go from 1 to 10.
Okay.
No. That's crazy.
It's a big number.
But you'll see what happens if you do that.
I would make your interval a whole number of, yeah,
So
divisible by that in that range.
should I keep
1.
0.2 or 0.1?
I would go between 2 and 3 at 0.1 as a start.
Sorry, I lost internet here at the wrong moment.
The way I usually do these grid searches, I start very coarse and very broad, and you get a general shape of the error surface, and then you can find where the optimum is, the coarse optimum is, and then you can focus in around that. That's the way I typically do these things. But
Okay, it makes sense now. Cool, thank you.
But Gareth says it's crazy to go from 1 to 10, so try 2 to 3, and maybe that's less crazy.
Okay,
Crazy.
I will.
It looks like you hadn't run the notebook from the beginning or something, so it doesn't recognize your NumPy.
Yeah, true. So there was a reason I just left it for later. I would do it later then. That there was a concern about the range.
Got it.
Yeah, cool.
All right. What else do we have for chats that we haven't answered yet? If you put in a chat and we missed it, because there's so many, just feel free to either type it in again or unmute yourself and ask the question. What is the command to recheck the password? Which password are we talking about? And what are you trying to recheck about it? The Earth data password? That's Faizan. So Faizan, what's your question there?
Oh, terminal password check.
I was just making sure whether my password is right or wrong given in the terminal. So I wanted to ask Gareth to write a command to check the password in the terminal. So
you're talking about the password that's in the netrc file?
yes, thank you very much.
Oh, did Gareth answer it? Oh, I see. That's what you mean by check. Okay. Okay. There's a question, is there a way to save the final results in a file? Lat long rates. So there are a lot of files associated with StripMap app that are created in a folder tree. Have we gone over those?
Can I ask you that question?
Yeah.
I got this result for California. It's I tried to get full seismic signal of El Mayo Kukapa earthquake, but first of all, I don't know how to plot the latitude longitude axis, and I also wanted to plot star on the epicenter of that earthquake, but these were very hard for me using GDAL. I used GMT, so I wondered if I can save results in a file that I can use with MATLAB or Pandas, that I can boost the process or do something after for geophysical modeling more easily. That's why I wonder if there is a way to do
Yeah. So did you run the GDAL notebooks?
Yes, I did. So
then you can use GDAL translate to make a TIFF file out of. Oh, you did that? Okay.
yeah, I tried, and then
you have to select band 1 maybe.
band 1.
Yeah, there were 2 bands in the. I don't know whether it. Does anyone remember whether it goes from 0 or 1?
I don't remember.
So what do you get when you do that? Band 1, band 2. Okay, there's band 2. All right. Okay. So in which case?
So is it correct?
Yeah, it should be. Yeah.
Yeah. Then I tried to convert it to Google Earth file, but somehow I cannot do that.
Can you? What do you use for your GIS?
I got this. But
the other thing is that you can save to GMT format directly using GDAL translate.
So I can put GMT here.
I think so, yeah, and GRD at the end. GRD is the file name, file type. You have to run it, of course. You scroll back up. Test geo.grd, yeah. Have you run that cell?
Yeah.
You haven't, there you go, yeah. So try plotting that. The other thing with your interferogram is that it covers the Gulf of California, and so there's a big body of water there that, in case you're worried about like not having.
I try another path, but I got really weird signal, which is this.
Yeah, I've seen that.
So
I'm wondering if it's soil moisture or something. It's definitely a feature that you get in those interferograms. It's a big dry lake bed, the Laguna Salada, and it's also a basin, so it could also be atmospheric, tropospheric. But I've definitely processed that interferogram a long time ago, and I see that. So you might not be doing anything wrong.
It was my cheat sheet, I think you're one of the co-author, and I expected to get like this nice result, but somewhat different. But I tried at least.
Yeah. Looks familiar.
It looks like it basically worked. So good.
Thank you.
So Parvis says he has a question about the strip map section result. Has that been answered?
Hi, can you hear me?
Yes.
Okay, I have a question about yesterday results, and maybe it would be better to share my screen. Is that okay?
Yeah, please.
Okay. Can you see my screen?
Yep. Yes.
This is the last result we got from a strip map using AGLOS satellite.
Yes.
And the final results looks a little weird. You know, there is almost 3 fringes here. I'm not sure, is this a systematic error or is just a stratified atmosphere? I'm not
Yeah,
sure.
so you need to wait for the afternoon discussion. So you will find that that's ionosphere, and you'll go through the process of removing that and leaving just the signal of interest.
Oh, I haven't seen that the ionosphere would be that much. I assume that it's more, you know, smooth and correlated in space, but it causes 3 fringes almost here.
There are some
Oh.
places where you get quite a bit of ionospheric ramps. And so, Gareth, your all caps, is that excitement or is it yelling?
Ominous, ominous.
Okay.
Okay. And that's what's weird because we fed it into the phase unwrapping and it got it as a signal. So I guess it would be removed before just using unwrapping software on that, because the actual signal is high, you know.
The unwrapper is not smart. It doesn't know what's ionosphere and what isn't. It's just going to unwrap the phase as it sees it.
Yeah, you're right. Okay, thanks. Great. Thank you.
Mm-hmm. All right. What else? How to convert unwrapped interferogram to wrapped one. In the Akmak notebook, unwrapped phase is divided by 10 before dividing by 2 pi.
Yes, because in the mostly because if you go back to recording, I think we said that in the beginning, the we converted the line of sight definition. It's presented in the unit of millimeters. That's why it's divided by 10 first before it's divided by 2 pi lambda or 4 pi lambda.
I do everything in meters, me. And I have to convert between centimeters and millimeters, and
there's no specific reason for it other than the notebook I stole this from was in millimeters.
All right, and Mohammed is asking for a quick few-minute tutorial on the XML files for Strip Map app. So, does somebody want to do that? What specifically about that is confusing to you, Mohammed? Just trying to think. In the notebook, it actually talks about the structure of those files, right? Have that up.
Yeah, true. I just saw the notebook at the very end, and I just just found out that we have a good tutorial that explains everything.
Yeah, okay, so you found that, and so you don't feel you need the tutorial anymore, or?
Well, I'm not sure, but I can try, and then maybe if I had some questions, I can ask later.
Yeah, there is a lot of documentation as well. I mean, basically you specify the, I can share my screen. There are a lot of options that are probably not fully described in the notebook. But at the bottom of the file, as you say, there's a control file and there's the data files, right? And down here, you can see in the understanding the XML file section, you can specify lots of different properties in the control file. And these are all sort of listed here and how they are formatted. So if you want to specify a region of interest for processing, you can specify it that way. You can control in the formation of the interferogram how many pixels to use in the range direction to average, and how many pixels to use in the azimuth dimension. For the output posting of the interferogram, you can specify that through that posting command. When you're doing the phase unwrapping, often people find that filtering the interferogram to remove noise first will create a better unwrapped phase product, or a more continuous and complete unwrapped phase product. So this allows you the ability to set the filter strength for that filtering to make it smoother and smoother. It defaults to 0.5. Usually 1 is the largest one we want to go with this particular filter, and 0 is no filtering. So you can play with that. Is this the kind of thing you're asking about? Just you can read through these things. If you're confused about a particular parameter, what it means, we can answer that. There's a lot of flags for just specifying whether to do a particular step or not. So whether to do the unwrapping, true or false, and which unwrapper you want. I think Gareth pointed out, or Haresh pointed out, we have ICU and snafu as 2 options. I think there actually is a 3rd option, but don't remember the name of it off the top of my head. Whether you want to do rubber sheeting or not, by estimating azimuth offsets and parameters for that rubber sheeting, and whether to do dense offsets or not. These are the parameters for setting, defining the dense offsets. Any of the interferometric products can be geocoded, and you can specify which ones in a list here. Similarly for that, offsets. Whether to do the split spectrum or not, this will be discussed this afternoon in the ionospheric section. And I don't know what dispersive phase estimation is. Does anybody know what that is? I would think that's part of the split spectrum, so I'm not sure.
Sounds like ionosphere, doesn't it?
Yeah, I would have thought that's part of split spectrum, but maybe they broke the, maybe this creates a separate file rather than just correcting the interferogram for the ionosphere. It creates a separate file that writes out the ionospheric phase for you. That's probably what that is. And then you can control some of the filter parameters for that. So these are specialized things that you'll probably not get into right away. And then for the data, they have a particular format where you specify whether it's the reference or the secondary image. And then you type the name of the file. directory where it can be found, the orbit directory. This is for the instrument characteristics. So for NVSAT, you'd have an instrument directory that specifies calibration parameters and the like. This is where the orbit data exists, and then the name of the output file, which is just a date in this case. And they all have similar kinds of structure, as you can see down here. In the case of ALOS, there's an image, a leader, and a leader file, both of which are needed. The leader has a lot of parameter information in it about the image file, so you need to specify both. Cosmos SkyMed comes as HDF5 files, which has all of the metadata sort of packaged with it. And looks like TerraSRX comes as a XML file, which I guess references other files in a folder tree. So it's pretty straightforward to specify the data, and I think the defaults for all of these other control parameters up here generally get you a reasonable interferogram, but you can play with them. And the help command and other documentation should guide you through the details of that as you get more and more familiar.
Thank you. Good to know.
Okay.
Yeah.
All right, it's time. So I think we move to the first item on the agenda, right? Do we have a break first, or did we just blow through the break? Oh, we were supposed to have taken a break. No, maybe not. Yes, we were. So do we want to take a break or just plow into it?
Let's take a break.
Okay, 10-minute break. We'll start at 10:10. I don't know if Melissa's still on, if she can put up the timer again. That was convenient yesterday. She is. Thank you, Melissa.
Thanks for all the questions.
Okay, we're recording. So it falls to me next, I think, to take you through interferogram interpretation. And we're going to use some real data of an earthquake and try and get you to interpret the interferogram. That's the idea. Right, I will share my screen. Hopefully I'm showing the right one. Good. Just as a sort of preliminary thing, just to go over yesterday, what we showed, the very basic idea of InSAR is that we measure phase change between passes of a satellite, and the measurements we make are in that direction, the line of sight direction. One thing to add, just to emphasize that the displacements that we measure are in terms of interference fringes. Each interference fringe represents a phase shift of 2 pi between the two passes of the satellite. And that 2 pi phase shift corresponds to half a wavelength of displacement of the ground in the line of sight direction. And if you think about it, a half wavelength of displacement towards or away from the satellite results in a full wavelength of path length change between the satellite and the ground, because the radar has to go all the way to the ground and all the way back again. So half a wavelength of movement of the ground equals a full wavelength of path length change, and that's why we divide the wavelength by 2 when we do these interpretations. That's just one thing I wanted to mention, just in case that hadn't stuck. So what we do when we look at interferograms is we try and count the fringes. Really, that's the process of understanding the total displacement of the ground. And so, as I mentioned yesterday, there's no sort of hard and fast sign convention about which way round the ground should be moving. So you hope that whoever produced the interferogram tells you this. And so I have done my due diligence and have put a big box saying what the sign convention is for this particular interferogram on the interferogram itself. So this is an earthquake that happened in Nevada in 2008. It was a magnitude 6. It was everyone's favorite earthquake who worked on the EarthScope project because it happened right in the middle of this very dense seismometer deployment across the entire mountain west of the US. So it's very well studied, and the interferograms are very nice. So here it is. It's a cute little thing. The way that we go about interpreting this, though, is to start by picking a 0 level. So I'm going to pick this fringe to be 0 displacement. It's kind of far from where the bulk of the action is, and it's a fringe boundary. So we're going to say this is 0 millimeters of displacement. Now, as I said, I've given you the sign convention here. Each cycle of blue to yellow to red is 28 millimeters of displacement away from the satellite. Okay, so let's count colors: blue, yellow, red. Okay, that's one fringe. And that next fringe represents 28 millimeters of movement of the ground away from the satellite with respect to the first fringe. You can go blue, yellow, red again, and there's 56 millimeters of displacement. Blue, yellow, red, 84 millimeters of displacement. Blue, yellow, red. Well, let's just say for the sake of argument that you can do that again, and 112 millimeters. Okay, so the total displacement, or the maximum displacement of that is shown in this interferogram, is about 11 centimeters, and it's a movement away from the satellite. This is an ENVISAT interferogram. ENVISAT had its incidence angle 23 degrees to the vertical. So it's approximately vertical motion, you could say. If you assume that the motion is vertical, it's not going to give you a very different displacement value. So let's just say for the argument that there's 11 centimeters of movement of the ground away from the satellite. The ground subsided 11 centimeters at the center of this pattern. And this fringe pattern in general is, well, here's a scale bar. It's about 12 kilometers long, this zone in the middle that moved a lot, and about 8 kilometers wide. I say that if this was an area where it rained, which it doesn't really because it's in the eastern Nevada desert, but if it rained here, you would form a puddle on the surface in this depression that this earthquake caused, that is about 12 kilometers long and 8 kilometers wide and about 10 or 11 centimeters deep in the middle. So this is the part of the magic of InSAR, that you would never be able to see that with your own eyes in person, but the radar can see it from space. That's pretty cool. And yes, this is a closed depression. You can see that these fringes are completely concentric. If you think about this as a contour map of displacement of the surface, then it's just a little sort of depression in the surface. And there are no sharp boundaries to this. So that's a way of us knowing that the earthquake did not rupture the surface and actually displace the ground more in any one location. Okay, so that's a little intro. The notebook that goes with this exercise has not really got any executable elements in it. It's just a web page really, but we can go and look at it nonetheless. It's in interpreting a coseismic interferogram, and there's the notebook at the top. I already had it open, I guess. It doesn't hurt to open it again. This is one notebook where the kernel doesn't actually matter, but it's opened with the UNAVCO kernel anyway. And there's some background information you can read here. What we're going to look at is an earthquake of an interferogram of an earthquake that occurred in Turkey in 1995. And here it is, included in the notebook. So there's a few things going on here. You can see that there are a lot of fringes. Those are related to the earthquake. There's also a lot of decorrelation, which is not masked out here. And those mostly correspond to bodies of water, which do not return coherent radar information between the two passes of the satellite. It doesn't neatly cancel out like it does, say, over these land areas. There's also some agriculture in here, which also has can have the effect of decorrelating InSAR, because if you have agricultural crops on one pass of the satellite and then you've cut them down, or you plowed the field or something on the other pass, then you get no similarity when you come to differencing the images, and those areas come incoherent as well. But what I'm going to ask you to do is to do the same kind of interpretation that I just did for the Nevada earthquake for this one. You can see that there are many more fringes, so that there's more to do. You can also see that on this interferogram, I've drawn a profile line. And what I would really like you to do is to interpret the interferogram along this profile, from X to X prime, and draw the profile of interferometric, rather line of sight displacement along this profile. Let's see. I have bolded the color scheme for you, the sign convention. Each successive cycle of colors from blue to yellow to red indicates an increase in distance between the ground and the satellite. So this is range change interferogram, 2.8 centimeters. We assume that the far field of the interferogram, the areas that are well away from stuff, basically have zero displacement. I've even drawn on a line here, which you can treat as being zero. So the start of the profile, actually at both ends, I didn't draw it on looping all the way around and wrapping around to the other side, but both ends of the profile are at zero displacement. What else? Well, okay. If you look in the directory, you see there are a load of other things in here. You can see there are PDFs, and there are PNG files, and also KMZ files that show all these things. So if, for example, if you click on these links are live, you can click on this and get the interferogram as a PDF. All the same things and the same caption and everything else. That's great. But you also, if you click on the second set of files, you also get the profile I would like you to write on. So these two files are to scale, which means if you print them at the same scale, the profile line on the diagram is the same length as the profile line on the interferogram. And actually, if we were all meeting in person, we would be handing these out as pieces of paper rather than trying to do this all electronically. And if you have access to a just put my chat window here. If you do have access to a color printer, you could, at this point, download these two PDFs and print them, and do the whole thing on paper, because I think it's easier. But so what you basically been tasked with doing, here is X and X prime for the profile, and you would want to mark on this chart the line of sight displacement as you go along the profile line. You also see at the bottom here an elevation profile, which shows that the southwestern end, which is near X, is low, and then at some point there's a steep rise in the topography and a little mountain. There's a 800-meter elevation change between the bottom and the top of this thing. It's pretty dramatic, steep ridge, and it turns out that the fault is located at that ridge, the fault that caused the earthquake. If we go back to the diagram here, you can see that there's also a black line marked on here. This is the location of the fault. This is actually a big discontinuity in the interferogram. If you look on the southwest side, lots of fringes. On the northeast side of that line, many fewer fringes. That's something to be aware of. It says somewhere in the text that that geologists in the field went and mapped this, and there was a 25 to 30 centimeter offset in the ground at the location of this line, so that every part of the ground to the northeast moved up with respect to the ground to the southwest by about 30 centimeters, or vice versa. The southwest side went down 30 centimeters with respect to the northeast side.
Gareth, there's a question in the chat about ascending versus descending tracks and how that may affect. It says the interpretation of the line of sight displacement, but mostly the appearance.
Well, it does have some effect, and we'll talk about this more I think tomorrow. I don't know actually when my next session is. I think it's tomorrow morning.
Oh, that's right. Yes.
Yeah. It depends on the sense of motion, I have to say, in the thing that you're measuring. In that vertical motions do not change between ascending and descending viewpoints, but the horizontal displacements will resolve differently. So if you had something that was dominated by vertical motions, you wouldn't see a big difference between ascending and descending. You would see some difference because almost never do you have a purely vertical motion. There's always some component of horizontal motion that accompanies it. But dominantly vertical motions will appear very similar in ascending and descending interferograms, whereas displacements that have some horizontal component, especially an east-west horizontal component, their contributions to interferometric phase will be reversed between ascending and descending. And of course, we just see the kind of the cumulative line of sight displacement. Really comparing ascending and descending data is one way that we can use to figure out whether there's any horizontal motions or not. And I do have more on this tomorrow. So if I still haven't answered it tomorrow, feel free to ask much harder questions. Okay, so as I say, what I would like you to do is to interpret the change of line of sight displacement along this profile line, and I've included, I think somewhere, where is it? Oh, it's here. Okay, so there's a few tasks you're tasked with completing, and you can fill it out in the notebook. You can double click on these cells and you can write in the spaces where I've given you places to write things, what your answers are. The first set of questions are all about counting the fringes, actually. And I refer to, I use some geological terminology, hanging wall and footwall, because I am a geologist, but I understand that many of you are not. I also define what they are. This is terminology that we use to describe the blocks of material above and below faults. And the terminology comes, I think, from mining. And so here's my way of remembering what a hanging wall and what a footwall are of a fault. So here is a diagram of a normal fault. I guess this was the most common type of fault, where the miner, among the people who decided these were normal. In a normal fault, one block of material drops down with respect to the other, such that the whole of the block of material is being pulled apart over time. And you can imagine you have a coal seam, you're mining here, maybe this dark unit here, and the miner mined through the coal seam, found that he was on a fault, mined down the fault plane, and then hit the coal seam again. I think this was kind of what happened. And then they gave names to the block of material that they were standing on. The footwall, that's the block with your feet on it. And the block of material above your head, above the fault, is the hanging wall. And you can hang your lantern from the hanging wall. So, okay, hopefully those terms are not too crazy. So it's also shown here, the footwall and the hanging wall. One is below the fault, the footwall is below the fault, and the hanging wall is above it. And you're asked to count how many fringes there are on the hanging wall side, and I can tell you that's the southwest side, and how many are on the footwall side, on the northeast side. So that's the first thing. Count the fringes. Count from 0 out at the end and count the number of fringes. And convert that to displacement and tell me which way the ground moved in those two areas. And then the next section is about the profile itself. And what your task for doing is, as I say, marking on the profile diagram where all the displacements were. And there are various ways that you can do this. Like I said, you could print these files out and then do it on paper. You can open the PDFs in various softwares that are capable of opening it. Illustrator, Affinity Designer, CorelDRAW, Inkscape. These are all will allow you to open PDF files and manipulate them. So you could do it that way. And if you don't want to do that, and you prefer a sort of a more bespoke solution, I made a Google Draw document. It's linked in the file. You can click on it, what it will do is it will load these two images, and the interferogram is rotated in such a way that it sits aligned with the ends of the profile, and then you can drag and drop these little dots to where you think they should go. So for example, I've gone half a fringe of displacement here. I'm going to put my dot about there. So if you're going to do it this way, please save your own copy of this. So make a copy, and then you'll have your own one to do, and you won't be messing it up for everyone else. Although I don't think anyone else has write permission for that file apart from me. So go off and make your own, and you're looking for the locations of fringes and where they correspond to positions on the profile line. There are also some hints that are given here. One is that the fringes are 2.8 centimeters per fringe, as we said. And at some point, it's probably easier to think about multiples of fringes rather than individual ones. I certainly don't have the patience to go and put a dot down for every single fringe. So 5 times 2.8 is 14. So 5 fringes equals 14 centimeters. So you could do it in fives. That gives you a nice multiple to go through. And you can also see that you could do 2.5 fringes is 7 centimeters. So think about that. Where the fringe gradient is large, counting every fifth fringe, as I say, is reasonable. And this final one is one that people never listen to me, but I always say it at the beginning, so I have plausible deniability. Rather than try and track displacement across the discontinuity, across where the fault is, instead consider the two ends of the fault separate, the two sides of the fault separately. So for the southwest part of the profile, start at the southwest end, and for the northeast part of the profile, start at the northeast end, and count inwards towards the fault. And don't try and unwrap across the fault, because this is actually essentially an unwrapping exercise. What you're doing is converting line of sight fringes into line of sight displacement. And once you've done your profile, you can tell me what the total vertical motion between the largest displacement on one side of the fault plus the largest displacement on the other side of the fault, what the total is, and what the ratio of uplift to subsidence is. And finally, this is getting towards trying to convert this into a geophysical model almost. So elastic modeling of the interferogram suggests that the fault that is responsible for this earthquake is a planar surface dipping at 40 degrees. So so the earthquake really was motion on this fault surface, not just pure up and down. Right? The up and down is a result of the motion on the fault. So can you use trigonometry to estimate from the vertical motion what this slip on the fault was? And at this point, unless there are any questions,
There's one question in the chat from Quinn. What's the advantage of interpreting wrapped interferograms versus unwrapped interferograms?
Well, how do you think we make unwrapped interferograms? Is one thing I would say. This is the process of unwrapping, basically. I think it's helpful to go through the thought process at least once to see what has to happen to be able to go from a wrapped interferogram like this one to an unwrapped interferogram. It's a good sanity check if you can interpret the wrapped interferogram and then compare it to what you get from the unwrapped. Because a computer does the unwrapping, maybe not thinking about it, just blindly applying some rules, and sometimes you can get results that are wrong because the computer made an incorrect assumption.
Yeah,
Where is the Google?
Oh, I would say two more things. The benefit of looking at the wrapped interferogram the way you see it on the screen is that it first of all, it shows you data quality often a bit more immediately. Once the data set is unwrapped, the unwrapper will apply a bit of filtering process. So you sometimes may unwrap across areas where the coherence is actually quite low. Looking at the wrapped interferogram gives you, I guess, a bit more of an immediate sense of where the data are trustworthy and where they're not so much trustworthy. The other thing that's of benefit of looking at the wrapped interferogram also, it's sometimes because in the wrap case, the sort of the color range that you're plotting is defined between -pi and pi, and it's fairly narrow. You sometimes can see small local variations of phase a bit more clearly as once the file is unwrapped. You may understand, if you look at this case, there's a lot of deformation that's going on. Once you unwrap this, your plotting range, expands quite a bit. And at the large plotting range, it sometimes visually hides some details that you often can see a little bit better when you look at the wrapped interferogram as well. So having a side-by-side analysis of the unwrapped and the wrapped file can sometimes be useful.
Yeah, it's like any homework. It's to help you get accustomed to understanding the intrinsic properties of the data. And if you go through this exercise, you will immediately see, oh, these fringes, I cannot figure out how to get across them. I need to go the other direction to see if I can construct the profile, that kind of thing. So it's to build intuition.
Someone asked where the document was linked. You scroll down. It's the Google Draw document is linked here. This is a hyperlink. You can click on it, and you'll get to see this. Like I say, you can make your own copy of it using from the file menu here. This kind of assumes that you have a Google account. I also should have mentioned that I included a line for you, so you can drop it on your diagram and then line up your dot with that line there. Another thing to mention is there are some places where there's decorrelation at the location where the fringe would probably be. For that, you just have to make your best eyeballing interpolation by eye of where you think it would be. Maybe there. That's where the fringe is up here, and use that. How can we count the fringes at the epicenter? Well, try. Try your best. Yes, it's difficult. They get close together. That's why I suggest counting them in fives. They can be counted by eye. We get pretty consistent within ±1 from people who have done this exercise themselves. As I said, you can also look at You can look at the file blown up large if you want. You can get the go to the PDF and zoom in like crazy if you want to. Then you get to the resolution of the interferogram close enough. But anyway, what I meant to say at the beginning of this is that you have until 10 till the hour to do this, which is the scheduled end time of the session, and maybe we want a couple of minutes before that to discuss the results. So don't wait for me to tell you to start. please get on with editing with making your profiles, counting the fringes, and editing your notebooks. What else is in here? There are vertical distortion trends in interferograms. Are these faults too? I don't quite know what you're getting at there. Maybe some clarification of the question would be good. Close to the marked fault, there look to be some tears in the fringes. Like here, maybe. It's probably part of the surface displacement of the Earth. You know, unmapped surface offsets, perhaps. I'm sure lots of you know that these days we use discontinuities and interferograms to send field geologists out to find more surface ruptures than we originally identified. So that could well be a place where you would want to send a field geologist to look around here, because it does look awfully like there's a surface displacement there. It's a very sharp change in the character of the fringes, which could well be a surface offset.
Happy mapping.
Yeah, happy mapping. Let us know if you're done. There's no prize for finishing first, but it gives us some idea of whether we can carry on talking or start talking again. The fringes on the southwest of the fault are very dense, while the fault in the north is less dense. Well, it's like if these were contours, and fringes, of course, can be interpreted as contours of displacement. What do you interpret from having contours close together versus spaced far apart? Emery asks, what exactly is the reason for the discontinuity present in the fringes? I don't know if you mean the decorrelation or the actual difference between the two sides of the fault. Does the Draw.io extension work at your site? I haven't tried it in a long time. It worked previously, but it's a lot more fiddly than using Google Draw. So Google Draw is the preferred method. So back to Emery's question, if you mean the decorrelation, there are a series of lakes in this area, and rivers also that cause decorrelation, and there's also agriculture. Yeah, so that's decorrelation, the speckle-like parts. So yeah, mostly terrain change between the two SAR acquisitions that make the interferogram. Water does not provide stable phase returns in this area, so we lose signal where there's water at the surface, and also if you have agricultural activity, often that changes the character of the ground between successive passes of the satellite. I think this interferogram spans several months because it's from the before Sentinel times, when we couldn't rely on there being a routine acquisitions like we can today. Let us know in the chat if you're close to finishing. Okay, we have people who are starting to get near the end. I should ask Paul and France what you think we should do here. We give people a few more minutes.
Yeah, let's give people a few more minutes.
And then have the wrap up at what, 11:55? Then
Yeah.
we'll only be about 10 minutes late.
I think that's fine.
Catherine is a little confused about the last question. Might help to draw on some scrap paper a right angled triangle. That's the question about slip. You know what? If you assume that the total displacement is vertical, then can you convert that into fault parallel displacement or fault slip? You would be assuming that the vertical motion you see is the vertical component of slip on the fault. I do have a diagram later on if you're.
Yeah, that's going to be great to discuss. When I ran this exercise in my SAR class this year, there was a bit confusion where the right angle goes. You know,
Fair enough.
project onto the line of sight. That's not always easy to wrap your head around. So.
I stripped almost all of the geology out of this exercise. There is a lot more in the full length version of this. Which is available as UNAVCO sponsored teaching materials for active tectonics. I think the link is somewhere in the notebook for that.
While we're waiting, since there's silence, I have a random question about the use of InSAR versus IFSAR. And every time I try to send like highlights to somebody at NASA, they always change it to IFSAR instead of InSAR. Is there a convention or why?
People who have been in the field for a very long time, who are stuck in their ways.
So in my personal opinion, which of course is the only one that matters, IFSAR should be eradicated. I think 90% of the community has agreed on IFSAR as being the term. On INSAR, sorry, oh, God, on INSAR of being the right term. IFSAR is mostly stuck in the heads of people that have started working with airborne radars.
Okay.
It seems to be more prevalent in the airborne INSAR community. But yeah, so INSAR I think is the standard.
What does the F stand for in that case?
It's still for interferometric.
Yes.
Oh, okay. Just the second letter or the whatever second syllable instead of the okay.
The same as, well, I don't know, there are people also that insist on saying DINSAR, which is technically correct, but life's too short to like make a distinction between INSAR and differential INSAR.
But you point at an important point. If you come from the outside, there's we are not very good at keeping our language clean. And so it can be confusing. So we used to be discriminating, for instance, between INSAR and differential INSAR much more than we do nowadays. differential InSAR sort of went by the wayside over time.
I once wrote a paper where we just said, we're just going to say InSAR. We know it's technically differential InSAR. That's okay though. It's mostly engineers that care about that. If Paul is listening.
Well, I could go on for about an hour on the politics behind this, but I don't think it's worth it. The IFSAR and INSAR are the same thing. IFSAR was sort of a military / airborne designation early on. The F is the F in interferogram. So, and we had a program back at JPL in the early 90s called IFSAR-E, which was with DARPA to develop some X-band interferometer. Generally, IFSAR systems were not like repeat pass, they were topo mapping systems. So often the distinction was preserved between IFSAR and INSAR because you could think of the IFSAR systems as the topo mapping systems and the INSAR systems as the differential systems. Differential INSAR, DINSAR never made sense. That was a Kness thing because already interferometry is a differential process. You're taking the difference between two image phases. So it's, and the way they did it with the DEM as the third component of getting rid of the topography, it was truly redundant. Differential INSAR would have been if you took two interferograms and subtracted them, that would be actually DINSAR. But that distinction was also garbled because of Kness's insistence on a new term. So
Blame the French.
For now.
I like it.
What's that?
Blame the French.
Yes, I'm going to blame the French in this case.
Okay, I think our time is running out, so I'm going to move on to what I think I saw.
Do you want to? Does anybody want to share their screen? Do you want to?
Oh yeah, do you want to do that?
Does anybody have a result that they think is perfect? Putting a lot of pressure on me.
No pressure. I can stop sharing and someone can pick it up if.
Does anybody have a solution they want to share and discuss? Otherwise, Gareth can do it, I guess.
Right.
Sure. Yeah,
Go
right.
for
If
it.
you want to.
Okay, give me a moment. Is that right? Are you seeing
I see that. I like it.
There's even interpolation done. Awesome.
Yeah, I'm not sure I would have been so bold as to connect them, but yeah.
So yeah, basically I tried to count the every 5 fringes and then tried to line it up. And then yeah, there should be a big discontinuity between the left side and the right side, which would be the fault. That's kind of what I tried to put there.
You've avoided the pitfalls of counting the fringes all the way across, which some people do. So yeah, this is something like what I have, which is great. And how many fringes did you count in total? 21 and a half?
So on the left side, 21 and a half, and then on the right side, be half, 1, and then 2-ish to the end.
I think that's defensible. So uplift to substance ratio about 1. Okay, yeah. So about 10% uplift, 90% subsidence. And the vertical offset total 67 centimeters, which is not so far off the dimensions of the grid. If you get much bigger than that, you probably counted too many. So that's great.
Yeah, and so if you guys went through the exercise the way O'Reilly did, is you see that it gets really hard to go through this exercise very close to the fault. Fringes get really tight. There's some decorrelation coming in, And sort of the, let's call it the mechanical unwrapper, sort of the computer unwrapper, runs into the same issues. It gets really difficult when the fringe density is high and the phase quality goes down. So it gives you maybe a little bit of an appreciation how hard of a mathematical issue that is to solve, and how understandable it is that not every unwrapped interferogram is perfect.
Thanks, Riley. Let me have grab the screen back. Yeah, so I was just going to take you through the process kind of as I saw it, which is very much the same as how Riley saw it. So 0, it's marked there. The first half fringe is 1.4 centimeters. You have to kind of eyeball where that is on the scale. 2.5 fringes in is 7 centimeters. That's easy to mark on your plot. You have to interpolate this fringe because it's hard to see exactly where it shows up, and this one also. And then I started counting in 5s, like so. And you can actually see as you get close to the fault, as people have noticed, the fringes are much closer together, which means the displacement gradient is very steep. But you can also see that past this kind of maximum, it's got 21-ish fringes, the fringes kind of flatten out to the north and south of, or northwest and southeast of where you are, and actually may start to curve back again. It's decorrelated where that would have happened, but the suggestion is actually that you have, if you were able to count the next fringe, you might have to actually start going back again. You'd be recounting ones you've already seen in this area here. The displacement gradient might reverse. Anyway, okay, then you've got the decorrelated zone and the fault, and you wouldn't want to count across those. So instead, what we're going to do is start counting again from the other end. So 0, the first half fringe is about here, and in this case, rather than going from blue to yellow to red, you can see we're going from red to yellow to blue. So the sense of the phase change is now reversed with respect to what you saw on the other side. So this is actually should be plotting above the line, not above the 0 line, not below it, because now phase is reversed. We're going negative range change. Okay, next plot would be there, next point would be there. And that is a profile which is very similar to the one we just saw. In terms of understanding what's going on in kind of the broader sense, it's fun to play around with the Google Earth files if you have a chance to do that. You can toggle the interferogram on and off and see what you have. The area which I said was uplifting, with the negative range change is actually located on a mountain. Or at least a steep ridge. The area where we see downward movement, subsidence, is on the side where you see lakes. I think this should be somewhat in keeping with what you would expect, right? The ground is moving down, that creates a basin, water flows in, you create lakes, and those lakes decorrelate. You can also see people asked about some of these things. If you found an interval that actually spanned the time when this interferogram was generated, you might see that there was agricultural activity in some of these areas which decorrelated, that are not where the lakes are. We see the lake is here. That's an area of decorrelation. So in general, yes, the areas that went up were the areas of high topography, and the areas that went down are the areas of low topography. And that would be in keeping with what geologists would expect for this type of faulting in this kind of area. So converting between uplift and subsidence, we saw these numbers, or something very close to them before. I go back and forth on whether it's 21 or 21.5 fringes, but it's about 60 centimeters down and about 7 centimeters up. And one thing to note is that it's smaller than what the geologists measure at the fault, 25 to 30 centimeters I mentioned. The reason for that, of course, is that where our maximum subsidence is not actually at the fault. it's actually offset some way from it, which is a way of saying really that the displacement on the fault at depth was more than the displacement on the fault at the surface. So the amount of slip petered out towards the surface, which is why you don't see the full displacement at the fault. And then the question about how to convert this to slip, you could draw a right angle triangle with like so, with 0.66 meters, say, on the opposite side, and 40 degrees at the angle here, and then it's just dividing 66 centimeters by the sine of 40 degrees, and you get about 1 meter of slip. And that's the answer. So those are the sorts of things that is how, for example, motion that is not exactly aligned with the line of sight, or can map into can give you a different amount of displacement from probably what happened on the ground. Are there any questions about any of that? Lost my chat window. Yeah, stop sharing. Must have made perfect sense because no one's asking any questions.
We should probably take our break now since we're
Yes.
a little behind. Maybe come back at 12:15.
I like it.
And then Haresh can start up with the TOPS app, and people can think of questions and put them in the chat in the meantime.
Absolutely. And I'll be at office hours this evening.
Excellent.
Well.
Thanks for playing
Thanks,
along.
All right. Cheerio. See you soon.
I hope
Say
most
eight.
folks got something close to what Gareth showed.
Yeah, we'll actually come back at 12:15, so a little less than the 10 minutes. Looks like you can't dial in. Oh, you can dial in. Okay.
Hi, Paul. Do you hear me?
Yes, please go ahead.
Right. And is it readable? I hear that even the video from yesterday was not high resolution. Is this one?
Where did you hear that?
In the office hour this morning, somebody mentioned?
No, they were talking about the video from last year.
Oh, okay.
Yeah,
All right.
I think this year's videos were fine. I think.
I hope so.
I can see it well and hear you well, Paresh.
Yeah.
All right. Thank you, Franz. All right. So we are going to talk about the processing, data processing with ISCE2 for TOPS data, and specifically from the Sentinel-1. This is a notebook that from a few years ago that David and Piyush really worked on, and I have made very minor modification for this year. Not much changes. So the notebook assumes some directory structure within the working directory. Actually, let me go back one more step and show you where is the notebook. I assume that you all know where is it by now. You are familiar with the course. So it's in GeoSync, UNAVCO 2021, 2.2 TOPS data processing. All right. So let me go back to the notebook. All right. So there is a cell at the very top that basically imports some utilities and some libraries like matplotlib, GDAL, NumPy, few other things that is going to be used throughout the notebook. There are some copy function from the S3 bucket, just in case if the download fails, it'll try to copy the files from the S3 bucket. But hopefully the download is working for everybody now. And there is some function for plotting the data. You can take a look yourself. So in the notebook yesterday, we were trying for each data set to write few lines of code to just really show you where the plotting is coming from. But the expectation is today you are familiar. If you are not familiar even before from yesterday, you should have some idea that we are using GDAL for reading data and we are using matplotlib for plotting. So now we have some predefined functions that we will just call them throughout the notebook. There are two of them, one for real data and one for plotting the complex data, as well as some stack data. So few plotting functions there. And then similar to yesterday for the strip map app notebook, we have also a configuration function, which basically sets up the input configuration file for TOPS app to be able to process data. In real life experiences, you have to either also automate similarly, or you might just use any editor and create an XML file similar to this XML file here, which basically is, I'm going to show that in a different representation shortly. Few functions on the query of ASF data, and I'm trying to replacing Sesara because it was very late when I noticed that Sesara is down. The developer is not probably anymore supporting through UNAVCO. But really, there is an excellent API from ASF that anybody can code up similar to what was in Sesara. I gave a shot. I didn't really have time to walk it through to make it to the end, but I will show you a demo of that. I heard in the office hour that maybe people still have problem with downloading data. Paul, may I ask you, do you prefer to talk about downloading data now, or maybe at the end when I'm done with this notebook?
Yeah, I think let's wait till the end to try to get through the meat of it. We have office hours and homework time tomorrow morning to do the more nitty gritty downloading stuff if people are having trouble. But
okay, perfect.
by the way, Haresh, is that in the Geosync repository? This is checked in?
Yeah, it is. Yeah.
Okay.
Yeah, it's to function. It's almost there actually. I can demo it later.
Okay.
This tutorial is about TOPS processing. As I mentioned very briefly yesterday, the acquisition mode, basically the imaging mode for the radar, is different from the street map. The difference is we want more SWAT widths. We want an image that covers more SWAT on the ground. Just to give you an idea, the traditional sensors like ELOS, ERS, NVSAT, they were all street map, and the width is around less than 100 kilometers, depending on they also have different modes. So I doubt if with any of them we get more than 100 kilometers. But there is a need to increase that SWAT, and TOPS is doing that by rotating the beam as moving along the orbit and changing the elevation angle to illuminate the next sub-SWAT, and rotating the beam again. And again, for the third sub-SWAT, change the elevation angle, so look even far, and rotate and come back. By the time that it comes back to the sub-SWAT 1, it will look back and it starts from somewhere here. So each of those acquisitions then basically is a burst. So you will hear a lot in this notebook that the TOPS data include some bursts. Basically, after focusing this data, we don't have one SLC, we have many. We have 3 sub-SWATs, similar to what I showed in that cartoon. So this is real data from ISA for Sentinel-1, TOPS data. We have 3 sub-SWATs, IW1, IW2, IW3, and each sub-SWAT has multiple bursts. They have packaged them in some frames. So basically one frame has 3 sub-SWATs, and each sub-SWAT has like 9 or 10 bursts in general. Each burst is basically one SLC. It has it's really just one SLC, but there are this figure might be a little bit confusing. In reality, there is actually overlap between the bursts. Each burst is covering around 20 kilometers on the ground, and the width is around 250 kilometers divided by 3, whatever it is, something around 70-80 kilometers. Basically, the total width of the SWAT then would be around 250 kilometers, and they are packaging it along track to another 250 kilometers. There are some resources if you want to learn more about the acquisition mode. This is the part that is basically needs to be replaced with just directly with the ASF API. But in the meantime, we have identified some scenes that actually we can just download from ASF directly. And if you want to follow the notebook with me, just go ahead and run this scene. I have run it before, and it's not gonna run that cell again for me. This is gonna be 2 scenes for Mount Cristo Ridge earthquake last year. There was a magnitude 6.4 earthquake in US. So Similar to yesterday, you have to set up the .NET RC to download. And if you have issue with that still, there were a couple of message exchange and chat on the Slack channel, so you can follow there for more instructions. So this is, again, this cell is gonna look if the data is not downloaded, if somebody has problem to copy it from the bucket, but hopefully the download works for everybody. We make sure that you are going cell by cell, so change the directory to where the tutorial is. And so I'm gonna just go ahead and do that. And if we look at that directory, then we see that there are 2 zip files already in that SLC directory. Just from the naming of the SLCs, we can see that this is S1A, Sentinel-1A. Sentinel-1 is a constellation. There are 2 satellites now, Sentinel-1A and Sentinel-1B. They are almost on the same orbit, so they are consistent from the very end users. It's really seamless. Nobody noticed because they are compatible. The orbits are very close, so we can combine. Actually, in this exercise, in this notebook, we are combining these 2 basically from S1A and S1B. We are making an interferogram between data acquired with 2 different Sentinel-1 satellites. And it's going to tell us that it's IW mode. There are multiple modes. This one is IW, which is the operational mode, and most of the Sentinel-1 images are acquired with this mode. It's an SLC. You know that ISA is releasing both raw data and also the SLCs. So we are going to start with SLC. So we are not going to do any focusing. Yesterday, I remember that we started with raw data and we focused the image. But here for Sentinel-1, we are just starting with already focused image, single log complex data. This one is telling us that it's dual pole V, so we have VV and VH in these data sets. We usually process the copole VV for interferometry because it's, in general, the copole channels give you better correlation. It's nice, actually, it's a nice exercise if you at some point try different polarization. And it tells you what's the acquisition date and basically the start time and end time of whatever is in this file. So there is some also utility to download the orbits. I included a script that automatically downloads the orbit for you. Again, when I realized that SASARA is not supported anymore, we had a script in ISCE. I just copied locally, so it's already included, and it downloads the orbit for whatever date range that you give. I know that the data that we are going to process today is basically somewhere between these 2 dates. So it's going to download all the orbits for those files for those dates, and eventually we need only 2 of them based on the acquisition dates. I choose those 2 dates. Basically, these orbit files precisely tell you each of them are covering what. This one covers from October 31st, sorry, from 18 March 2021 up to 10 May 2020. I'm sorry. No, that's the production. That's the production date, the date that the orbit was produced. Actually, recently they reproduced the orbits for Sentinel-1, so that's why those dates are so recent. But the actual state vectors of the platform, which time they are covering, is these 2, from this date to this date. So yeah, this first date is when the orbit file was produced, and these 2 are the start date and end date of all the state vectors, the positions of the satellite that it covers. We need only these two orbits, so I just copied them to the orbit directory, but that was really redundant. The Sentinel-1, the TOPS app finds the exact orbit as processes the data as far as the directory is given. Is there a question? All right. So there are some calibration files we ignore in this notebook. The Sentinel-1 SLCs are calibrated. However, you know, there are changes in the processor that may have not maintained consistency between SLCs processed with different versions of the ISCE processor. One of them was this version 2.36, where they introduced some changes. I think it meant to improve the backscatter of the SLCs, but it was introducing some changes to the interferometry as well, to the phase, and it was causing inconsistency. So for those old data, we needed to take those calibration files and take care of it. They are reprocessing the data, and I don't know if actually there are still old data that require this calibration. But anyway, just to be aware of it. For this notebook, we don't need it. And TOPS app is gonna give you a warning if the data is very old and IPF is a certain IPF, then you will need to have those calibration files. And then to set up the processing, we are using TOPS app.py. If you just say --help, it's gonna show you some general help similar to StreetMap app. That more to come as we are going through the different steps. The input configuration is XML, similar to StreetMap app and rest of ISCE2. Here is the TOPS app.xml, where you say, well, this is TOPS InSAR, and this is the sensor name is Sentinel-1. So we don't distinguish between A and B again, they are consistent. So we just say Sentinel-1. And for the reference image, we are pointing to a reference.xml file. For secondary, we are pointing to secondary.xml file. And you have different configurations. You can decide if you don't specify SWAT, it's gonna process all the SWATs in the data, all 3 sub-SWATs. If you want to process 1 or 2 sub-SWATs, you would put it here. The range looks, usually when we make the interferograms, I hope it's clear by now that they might be noisy for different reasons, that the temporal decorrelation is really dominating now the source of the noise for modern sensors, because the baselines are so small, so the geometry is very similar. It's so similar that barely contributes to any decorrelation. So mainly just because one image is now and the next image is 12 days later, the scene, the scattering properties of the scene has changed and you get a noisy interferogram. So, well, you need to multi-look as a filtering approach, right? So you can define how many looks you want to take, basically how many pixels. It's a window of 7 by 3, 7 in range direction and 3 in azimuth direction. The numbers, if you are wondering why 7 and 3, what's the magic there? Basically, the azimuth resolution for the Sentinel-1 SLCs is roughly around 15 meters. And the range resolution, the slant range, is around 2.4 meters. If we project it to the ground, the ground range is around 4 meters. So 7 looks takes us to around 30 meters. And 3 azimuth looks also, it takes us around probably some more than 30 meters. So I would choose less, but anyway, that's the setup here. So it's not quite a square in this example, but you can play with the number of looks yourself and how makes sense for you. You can specify a region of interest. It's more popular, this option, for TOPS app processing when you are processing on your laptop or your limited machine, or if you are interested in a small area, because the data is big, more than 4 gigabytes each SLC we have. So you might want to basically specify a region of interest. And based on that region of interest, then you will see that the number of bursts that are gonna be pooled for processing is gonna be limited. So in this case, you will see in the following that based on this region of interest and based on the fact that we have asked for only subSWOT 3, we are gonna process only four bursts. By the way, ISCE doesn't allow you to specify to process only a small region within the burst itself. So the processing unit is a burst, and we allow for more than at least 3 bursts. And the reason for that is in details that I go through in this notebook. It was a design choice, and because we need some processing for accounting for misregistration in azimuth direction, which needs few overlaps between different bursts. So you need more than 1 burst. And few more configuration if you want to do unwrapping, which unwrapper name, and if you want to do dense offsets. So if you can specify that, which is true for this example. Those configuration files, again, and here is the reference and the secondary XML file, which we pointed to in the TOPS app.xml. And we are pointing to an orbit directory wherever the orbits are downloaded. We don't need to specify the exact orbit name of the file. It's gonna find it as far as it exists there. It's a reference, and then that's the image that we are gonna basically the zip file for the reference image, and here is the zip file for the secondary image. Those XML files are gonna be created here just by running this cell, which is running the function, calling the function that I introduced at the very beginning. By now I have already processed, so you see more stuff, but reference.xml, secondary.xml, and topsapp.xml at least should be there for you if you are following and running these cells with me. So to start running, let's take a look at all the steps that TOPS app is trying to do, which starts from startup all the way to geocoding. We have some pre-processing, computing baselines, which is not really used anywhere. The baselines is just for general information. And then checking the DM, running RDR to geo. There is some extra steps compared to what you saw in the strip map processing yesterday. And those extra steps are specific to TOPS. They start from subset overlaps up to the ESD. And I'll tell you more about all those steps. And then after that, really things get a little bit more similar to what you saw in the strip map processing. However, somewhere we are merging the bursts. So note that in ISCE2, we try to keep the bursts as much as possible, as long as possible. So we keep the burst and we do the geometrical co-registration or refined co-registration, all burst-wise. And then we even do resampling on burst. We form the interferograms on each burst, and that's full resolution interferogram without any filtering and multi-looking. After that, and just before multi-looking, we merge them. So we make a bigger interferogram, a merged interferogram, and then we from there it's really similar to strip map and any other interferometry processing. So let's go along and see what we have. Again, some few more checking if those configuration files exist. Otherwise, it will try to pull it for you from the bucket, and make sure to run all those cells that says go to InSAR directory, and from there we start the startup and the baseline. If you look at this cell, which is the first step, first two steps, basically, it's if you look at the outputs, it says a number of bursts before cropping. There are 9 bursts for subswat. We asked for subswat 3, remember? And then based on the region of interest that we gave, it's gonna pool only 4 bursts. And it just, this is just for bookkeeping and indexing the bursts. So it's gonna pull from those 9 bursts, only 4 bursts. And by the end of this step, then, and also it's gonna compute the baselines, which is a low resolution grid of the baseline. By the end of this step, then you should be able to see if you have a terminal open. In the same directory that you have the TOPS notebook, there should be a folder called InSAR, and inside InSAR there should be a reference. If you look at the reference directory, you will see that there is a subdirectory IW3 and IW3.xml and overlaps. Well, you don't have the overlaps yet if you are following exactly those steps. So IW3 clearly is the third subswat that we asked for. And if you look at it inside, we see that we have burst 1, burst 2, burst 3, burst 4, .slc, .vrt, .slc, .xml. So we, in ISCE2, there is this functionality to not actually pull the data, the actual physical data from the zip files. We are just using the GDAL functionalities. And if you look at burst 01, .slc, .vrt, let me just print it. You will see that there is a link. It's a VRT file. If you have looked at the pre-course GDAL, VRT is a GDAL virtual raster table. It's an XML file basically, and it's pointing to VSI zip, pointing to the zip file, and within the zip file, which is here, we are pointing to the where the TIFF file is, which includes 9-10 bursts, and in that TIFF file we are pointing to exact line and pixels that corresponds to that burst. So basically we are virtually extracting those bursts. So that's an important functionality, and it allows you to save some space on your machine because these files are too big and very easily they get out of hand for processing. The other thing that I wanted to mention actually is by end of this step, you have also the excuse me. In the same directory reference, you see that there is also the XML file. That XML file has all the metadata that we extracted. So this is a format that ISCE understands. So all the metadata exist in that XML file. All right, so I'm gonna go along, and there are some pickles files as well. This is some container for storing some objects, basically, that ISCE is keeping track of for doing step-by-step processing. All right, I believe I already explained all this, what was also in the notebook, and you can read about it more if you want it later. All what I explained is there. So the next step is verify the DM. It checks if the DM exists. If not, it tries to download it from that's just this RTM DM, and you need your login password to be set up in the .netrc file. For this specific example, it's possible to pull it from the bucket if the download failed for anybody, and then you have to rerun the verify DM. And finally, the important step of the topo, it's gonna start in this step, very similar to what we explained yesterday. We are running the burst by burst and pixel by pixel, running the geometrical computation, which we call topo. It's basically radar, going from radar coordinates to the geo coordinates. So this is gonna be very similar. It's the same core module that we use in StreetMap app, but this time for each burst. So basically you will end up with another directory called geometry, geom reference, geometry of the reference image for each subswat. In this case, we asked only subswat 3, and latitude, longitude, height, and line of sight, which is the incidence angle and the azimuth angle for burst number 1. .rdr means it's in radar coordinates. So it's the geo information and the geometrical information, but for each pixel that is in the radar coordinates. So it's gonna do those computations for all the bursts. And again, after running, you have that subfolder, which then now you should have. It takes some time for you if you are gonna run them step by step. So we have long and lat and height, and for each of the bursts. You can run the GDAL info on one of those to tell you, for example, the shape of one burst is around 1,500 lines in azimuth direction and around 24,000, 25,000 pixels in range direction or crosstrack direction. And here is some plotting of the outputs for one of the bursts. We are showing the height 01.rdr. Basically, that's we solved during topo, we solved for lat, long, height. So this is the height above ellipsoid for each pixel in burst 1. And here is the height. Since it's the height, you can see the topography probably. And as you see, it's like 25,000 pixels in range direction, and it's a burst, so it's around 1,500 lines in azimuth direction. This is just the color scale for this topography map. We are also displaying the line of sight the band 1, which is the incidence angle. So that would be this one. Here is the incidence angle for one burst. And here is the color scale. It's not the best way to plot the color scale with the same size of the burst. Sorry, it's a little bit confusing. But this one is color scale, and this is the burst. The bursts are so small in this plot that they look like the color scale. And you see that the variation of the incidence angle from the near range to far range for this burst is around 42 degrees to 46 degrees. This is the subswat 3, so we are at the far range. We are looking far from the nadir. And the last, the second channel of the line of sight files that Topo generates is the azimuth angle. And you see that it's basically minus 99 degree, 99.7 to minus 99.2. So basically with the azimuth angle and an incidence angle, you have all the information that you need to project any in situ observation like GPS observations to project to the line of sight direction of your SAR data. So that's very common that at some point, actually you will see by the end of this course some examples that we take GPS data and we project it to the line of sight. And you really need to know what was your SAR geometry, and the SAR geometry, the line of sight is given by that line of sight file, which has incidence angle and azimuth angle. All right, so these few steps, which I have already let it run, and I'll just explain what's going on. It starts from these subset overlaps all the way to EST. If you are following, just try to run it, and I'll go through the explanation, what's going on in those few steps. So basically, one characteristic of the TOPS data is this rotation of the beam along the track to be able to solve some issues that existed in the similar acquisition mode, which was ScanSAR before TOPS. ScanSAR, similar to TOPS, looks at different subswats, but it doesn't rotate the beam. So the targets in each burst are observed only for a limited time, and that really reduces the resolution and the radiometry of the focused ScanSAR images. And there are some effects very well known as scalloping. So if you look at them, there are some wavy features of the basically the images are not in their best quality of the focused data because there was no enough data. But with this rotation of the TOPS, we solved that. So the images have higher quality, but also we get some problem with the burst boundaries, and we have an extra Doppler. Basically, that rotation means that we have an extra Doppler. That extra Doppler increases the sensitivity of the TOPS data to misregistration. So if you have let's say tenths of a pixel co-registration error, and if it's constant in a strip map data set, you wouldn't notice because we don't have that extra Doppler. But in TOPS data, because of that linear extra Doppler introduced due to the rotation, we end up with an equation like this, very well known, that you get a phase. Just, the phase is basically the integral of the Doppler, right? So if we have a Doppler and it's linear, and if we have a constant misregistration, it creates a linear phase ramp. So if you are somewhere in the overlap of two bursts, and if you have one phase ramp here and another phase ramp here, because you had a constant shift, it's one constant for the entire image, but you would see a phase discontinuity. So that's one problem with TOPS data. And in these few steps, the TOPS app tries to look at the overlap of the differential interferograms, double difference interferograms. So this is slightly different from the discussion we had before about InSAR, IFSAR. The double difference interferograms are basically, we have at the overlap, we have the reference image and we have the secondary image. And for the reference, at the given overlap, if we zoom in, we have some data from the from two bursts, right? So part of it is from the burst at the top and the other one from this same date, but burst at the bottom, and the same for secondary. So we can make one interferogram using the overlap at the top, let's say burst 1, and one interferogram with the overlap at the bottom, let's say burst 2. And so we have now two interferograms, and if we double difference them, basically if we cross multiply one interferogram by the other interferogram, all range related phase is gonna cancel out. So the displacement in range direction and all related to the range is gonna cancel out. 4 pi over lambda delta R that Paul talked about multiple times yesterday, and in multiple places probably so far you have seen it, that phase cancels out in a double difference interferogram. What remains is whatever displacement in azimuth is left, which could be either actual ground displacement or some ionosphere induced misregistration, or actually some processing errors in the focusing because of the approximations during the focusing, or it could be just, you know, a constant shift of the timing errors of the orbit or the clock or whatever. So if you are doing this estimation, ESD, it's called Enhanced Spectral Diversity Estimation, you should be aware of it, that basically you cannot distinguish between those different sources of introducing an azimuth shift. You are assuming that it's just a timing error and I'm gonna estimate it. But since, let me say this, when TOPS came and when we digged into this issue, then actually there is a publication that we have, and if you look at the plots in that publication, it's referenced in this notebook, you can find it, you will see that statistically they are not significant in many areas that we have looked at. And the paper goes back to 2016-17, and in last 4 or 5 years, the experience also showed us that really in many areas, it's negligible. So the geometry is precise enough that probably ESD is not needed, that extra refinement is not needed in many cases. However, there are also cases that we see burst discontinuities, and it turned out that actually many of them are not due to the timing error, but due to other effects, including ionosphere, including the azimuth ephemerate error that was introduced during the focusing to the data. So you should be aware of that. But since I was hesitant to keep it for this year or remove it, since it has more weight, at least in my mind, to always apply it to the TOPS processing. But since it has this value that the overlaps in TOPS are really an extra source of knowledge to tell us about azimuth displacement, I wanted to keep it and give you this perspective that, yeah, one way would be the way that it has been used in TOPS app is the traditional way for extracting the misregistration. But keep it in your mind that actually it has other values, including the extracting displacement in azimuth direction. And actually, I saw that recently there are a couple of literature on that. In case if it's not very clear for you why there is a value in that, our limitation with interferometry is the fact that we are looking at line of sight, and we are most sensitive to the movements in line of sight direction, and our orbits are near polar orbits, so we are going north-south. Our sensitivity is really to vertical and horizontal, close across in east-west basically, and vertical. The sensitivity of the interferometry with the current orbits that usually is near polar is not much to the north-south movements. So if you have a fault that is north-south oriented, then you might be interested to look at burst boundaries and try to get some azimuth, some displacement in north-south direction. That's the value there. It's touching the boundaries. But that's the reason that I kept this part in the notebooks this year. So I wanted to really tell you about it. I hope that I have not lost you too much details, but that's the specifics of the TOPS. And let's take a look at the results of these few steps. Here is an example that we show for one burst overlap. You see that the amplitude for basically burst 1 and burst 2, and that same date, but we have two bursts, they are overlapping, and that's the amplitude of the two. So they are very similar visually. And of course, the phase is just random. And the same thing for another. And here is the actual burst itself. So if you, what we did here in TOPS app, we try to run then the next step, GO2RDR, and estimate the compute the geometrical offsets for each burst overlap. So that's more efficient than running over the entire burst, because we are gonna use only the overlaps for refining the EST stuff and to refine the misregistration. Here is the offset in range for one of the burst overlaps. So you will see that now you are looking at the directory called coarse offsets, overlaps, subswat 3, range bottom, and we have another one, range top. So basically, and that indicates it's between burst 1 and burst 2. So we have those offsets, and we run, that's another example. Again, we run the resampling. Now we have the geometrical offsets for the overlaps. Still, we are not doing anything for the full burst. So still we are at the overlap, and we run resampling. So we get the resampled secondary images. And then there is a step, overlap interferogram. So we make the overlap interferograms, which is basically what I explained a few minutes ago. And by end of that, you get a lot of, in the overlaps directory, you get a lot of overlap interferograms. So here is some examples. We had 4 bursts, so we have 3 overlaps, right? And that's the magnitude, and that's the interferometric phase for those overlaps. But then
for each overlap, we have two interferograms. And that's where we cross multiply those, as I mentioned before, and we get the ESD or double difference interferograms. And from that, there is an equation that you can estimate the misregistration. In this case, we were interested in the misregistration. And here is just the coherence of the overlap interferograms. Once we have and that's the differential interferogram. So that's interesting. Let me explain this part. As you saw, here is the interferogram. And remember that this interferogram is over a region with an earthquake in it. I know that. And you already see, so by the way, this is just for display. I hope you are not, I hope it's clear that basically in reality between this image, we have three overlaps. And those overlaps between this one and the next one, there is a lot of data that we are not showing here because we haven't processed yet. So when we are putting them together, basically there is a spatial disconnect between them, of course. We are looking only at the overlap of the bursts. And there was some signal that you will agree with me at the end that this is really the fringes of the earthquake. But in the double difference interferogram, they are all gone because as I told you, we are just cross multiplying two almost same interferograms. But what is remained is really some noise, almost zero, and some blue areas here, which most likely is due to the azimuth displacement, north-south displacement that I told you. And there is a coherence that we usually, this is the amplitude, but we look at the coherence and we have an estimate with the equation that I showed you. We have an estimate of the azimuth misregistration, a histogram that we choose the median, and we only look at the pixels that have high coherence. And you can play with the coherence threshold in the TOPS app XML. So very, very similar to that step, we can also estimate a misregistration for the range direction. Because in range also there might be a misregistration due to the propagation of the microwave signal through troposphere and ionosphere. We might have a delay, and any geometrical co-registration will miss that. So you can, similar to yesterday I mentioned, you can cross correlate the two already co-registered SLCs to find that extra misregistration and account for it. In this case, we are using the overlap bursts to come up because we are interested only in one constant shift. So in this case, it turned out to be very, very small. I would like to maybe stop for 5 minutes. I am here if there is question, but what do you think, Paul? Shall we have a break for 5 minutes?
I think that's a good idea.
Okay, I'm here if anybody has question, but let's, it's 1:09 here. So in 6 minutes, 1:15, we can resume maybe.
Yeah, that's good.
For those who don't want to break, if there is any question, or maybe that's not a good idea because somebody will miss it.
Yeah, let's just take the break.
Okay, let's take the break. in the office hours.
Thank you.
All right. Well, I see that few had problem, but has there been anyone successful?
There's a comment that the topo step is taking forever. That's true.
Yeah.
The topo step is the slowest or the longest processing step.
Okay, somebody has got the geocoded results. That's great. Okay, yeah, there are few so far announced that they got the final results already. Yeah, as Franz said, topo step can be slow. That's okay. Yeah, so it should run. Perfect. All right, so let's continue. I'll go back to where we left. So far, I hope it's clear that basically what we did really is very, very similar to what we had in the StreetMap app and in general, in the general interferometry processing workflow, except that this was for tops and we had to take some extra care about the co-registration and this looking at the overlap of the bursts. But by now, we already have the okay, I think, yeah. All right, I believe we left off from here. So by now we have the misregistration, and now we are running the fine offsets all the way to fine resample. Basically, we say, yeah, we know how much geometry is off based on the results from the ESD and the cross correlation over the overlap bursts. And from there, okay, now compute the proper offsets between the reference and secondary, and resample the secondary to the grid of the reference image. So once that is done, then what we have is the fine offsets for the first step of it, because there are two steps. And that's very similar to what you saw yesterday, but this time burst by burst. So now we are out of overlaps. Overlap is done. We are back to burst level processing. And then after that, we have the fine resampling. There is a step that we are gonna skip today, but you are welcome to try it yourself. Our colleague Chandran Yang has contributed ionospheric phase estimation for TOPS data, and there is a step, you can just say -- two-step ion, and you will get to run that step if in the configuration file you have asked for, which we didn't today. I'll try at the end to, in the notebook, actually, there is a link to the example configuration and all the options, which is here in the ISCE2 repository. And those so it's in ISCE2 examples, input files, tops app.xml. And in the notebook that we are talking about, there is a direct link to this XML file. And it has all different options that you can play with, including at the very end, there is a lot about ionospheric phase estimation. The next step then would be burst interferogram up to filtering. As I mentioned, we are still at the burst level, and this step is gonna cross multiply the co-registered SLC of the secondary image by the reference image and make interferograms for each burst. This example, we have 4 bursts, so we expect to get 4 interferograms and their corresponding correlation files. And yeah, that will be all. So when you see burst 01.3 azimuth locks, 7 range locks, that's the wrapped interferogram. And it's already multi-locked. But however, we really need these full resolution interferograms because that's what we are gonna use for merging. We never merge the multi-locked interferograms because otherwise, if you try to merge multi-locked interferograms, you would end up with some edge boundaries because we have each of them separately. So here is one example of the multi-locked burst interferogram for burst number 3. And you see the magnitude, the amplitude of the interferogram and the interferometric phase. So some familiar fringes of the earthquakes are showing up. And the next, then at the same step, we have already done actually the merging, and the result is in the merged topophase.flat.vrt, and that's it's actually topophase.flat. But here is the merged interferogram. So we processed only four bursts, 1 subswat, and we know that that covers the earthquake. We already have it. This was a magnitude 6.4 earthquake, Mount Cristo Ridge in US, 2020. All right, so we can filter now. We can filter the merged interferogram. Here is a plot of the interferogram before filtering and after filtering. There are some general description that my colleagues have put in this notebook about, be careful with filtering. Usually, if it's for visualization, okay, we all like a cleaner interferogram. But the goal is that you should be aware that any filtering sort of is changing the data set, and smoothness is not always what you might need. It depends on your application. So you should be aware when you try to filter more, for example. There is a step, then we get to unwrapping and unwrap 2 stage. I believe we have turned off the unwrap 2 stage, but I will shortly mention because it's not relevant for this one, so we turned it off. So this is the unwrapped interferogram, unwrapped with snafu. Nothing has been masked here. There is a quality map called connected components, and this shows that most of the region is actually one connected component, which is blue. That's why blue is dominating this plot. But actually, if you look at closer, there are some non-blue, different colors. And in some examples, like the interferogram over Turkey that Garrett was showing in the previous session, I'm sure if we look at the connected component of that interferogram, you would clearly see that how many regions you would have, and different regions and water and the correlated areas are not properly unwrapped. So this is a relatively easy case to unwrap. But again, I would like to emphasize that take a look at this quality map, connected component, and it tells you how the quality of the unwrapping was. And maybe for the homework, you can choose a different pair, and let's see, maybe your pair will be more difficult for unwrapping, and the connected component then would be more meaningful for you to take a look. And finally, the last step then would be the geocoding, where we run the geocoding for the unwrapped interferogram. So, and what else? I believe that's just extra stuff. Oh, the pixel offsets. If somebody is interested in running the dense offsets, then this part could be also explored using TopSap. And for that, by dense offset, we mean that we have co-registered the reference and secondary images. And we usually merge the burst SLCs for this step. And then we run amplitude cross correlation on the reference and secondary co-register SLC to find the residual offsets. And those residual offsets, as my colleague Brent will go through it in one of the sessions in, I think, tomorrow, you will see that how valuable they are when the displacement is so large that you cannot really detect them easily with interferometry and only with phase information. So basically, this will be the steps that you would run to get to range offsets and azimuth offsets. In this example, the range offset, if you take a good look, it's similar to what we saw in the phase. However, generally, the pixel tracking is not as accurate as interferometry. So you remember that yesterday, multiple times, Paul mentioned, and also in other sessions probably, that in theory, we have the measurement accuracy of millimeter level with phase, regardless of, inclusive of all those components that are in the phase. But we have definitely more accuracy in measuring the interferometric phase. And so the displacement with phase, so the offsets are more noisier, that is totally expected, but they are also very valuable when we have large displacement, which then you cannot get with only phase. And here's the azimuth offsets. So there are two channels of the outputs. One is range and one is azimuth. And finally, we can geocode them and take a look at the geocoded results. Perhaps the color scale is not perfect, but some filtering has been also done here. But roughly, you can see that part of it is more towards orange and part of it is more blue. So I assume the fault was somewhere here. All right, so I think that will be it. And for your homeworks for this notebook, it will be great if you, first of all, I think everybody should be able to run the same notebook and then try with your own data set. Try to change the configuration files, the reference.xml and secondary.xml specifically. And you should be able to run it on your own data. I think that's how you will really learn how to process TOPS data with ISCE2 TOPSAP. You should definitely try to run on a different data set. Any question? I think we have time.
Yeah, there are a number of questions. There was one question about people that get Doppler estimates that are 0. Beatrice, maybe you can explain a bit more. I think there's a couple of people that have the same issue.
Oh, they are estimating at Doppler 0? Sorry?
It's just that when we are running the topo step, it just stays there forever. And my last line on the output says that I have a Doppler of 0, 0, 0. And so I'm not sure if that's part of it or if that's indicative of something going wrong.
No, the Doppler, I saw a question that what is the Doppler for these SAR images? So the Doppler of the focused image is 0, so that's fine. The geometry computation.
It moved.
Oh.
So yeah, I have again the same line, but now it has another line before it that says that it's on line 1001. It was on line 1 before, and now it moved 1,000 lines, I guess. So
just needed me to tell it the Doppler is fine.
Yeah, so it's just super slow. That's it.
Yeah. So I can imagine, Franz, do you know how many people are on the same machine? Yeah, I can imagine Topo could be slow.
One machine is shared by 2 people, but yeah, so it's yeah, it will take a little bit for all the steps to exercise, but they should complete fine.
Yeah, so if you are sharing your instance that you are on with your friends, your colleagues, whoever is on the course. So please make sure that you are not running like 5 different TOPS app at the same time in the same instance. So that definitely slows down for you and for others. So at max, at least for this notebook, just run only this notebook. Don't run more than one. All right. S3 is in development. What is the status of I3 and what will the major differences be? Yeah, I3 is the formal processor for ISAR. So the focus is really to be able to process ISAR data. So the significantly fundamentally difference is that it's the ISAR focuser, and it will produce the ISAR images from the raw data, which no other processor is able to do because the ISAR data is not out yet. Maybe when it's out, others will do as well. But that's the fundamentally different thing in that sense. The other thing for the core modules, there are similarities. The team has tried to rewrite many old modules that were mainly in Fortran. So now we don't have any Fortran in ICE3. There is only C++. And there are usually, whenever possible, there is a CUDA version of the C++ core module. And then it's a more fundamentally modular framework. So we still don't have fully Sentinel-1 compatible workflows there, but we are working on that, hopefully in future. But so far, the focus is on ISAR really. Good question, J. Kim. The SNAFU and SNAFU MCF. So I think I have to revise that myself. I believe one of them is SNAFU is trying to do some iterations on the solution, but SNAFU MCF is gonna stop at the approximate solution, which is good in many cases. But yeah, there are multiple ways that SNAFU is can be used. If somebody has more detailed information, maybe Yunjun, if you are online, you have recently unwrapped more interferogram than me.
I guess MCF stands for minimum cost flow.
Yes.
Sure, Paul knows more.
Sorry, what's the question? I was trying to figure out something else on that I'm having trouble with. What's the question?
The question
Oh.
is what the difference is between SNAFU and SNAFU MCF.
If I answered, I'd probably not get the right answer. But basically, SNAFU is not minimum cost flow. It's a different algorithm, but SNAFU MCF uses a minimum cost flow as the solver. So I don't remember what the name of the default SNAFU unwrapping solver is.
Yeah, they have the algorithm has MSTM, MCF, minimum span tree, and minimum cost flow.
Yeah.
I know that also there are different workflows there, different modes, and one of them is stopping somewhere, but the other one is trying to do some iterations. I believe so don't pay too much attention to the name that we have put in, SNAF1, SNAF MCF. It might not be fully meaningful and might both actually use MCF, but one has more iteration and one less.
If you look at the chat, there are questions about the azimuth and range offset matrices. Whether those are...
No, the range and azimuth offsets, I assume you are talking, Francisco. I think you are talking about the dense offsets. They are computed for the entire image. So basically, for the dense offsets, if you are talking about that, we merge the bursts and then compute the dense offsets. Basically, so it's slightly different from the interferometry workflow. Yeah, I think that is your question. Yeah. I see the Michael's. Okay, that's Garrett's responded. Is the output of the dense offset step another proxy to determine deformation, or we can use it to refine the co-registration step? So in the tops up workflow, we run dense offset twice during the co-registration. We run it only on the burst overlaps. That's where we were interested in only finding a constant shift in range direction. So in that case, that was for co-registration. But later at the very end, you saw that we run it for the entire image, and that was for deformation purpose. So at least in tops up workflow, that's how we are using it. One estimated offset value in range and azimuth would be enough to align entire burst. So the burst, we have a pixel by pixel offset computed using geometry. And that is very, very precise at definitely at centimeter level in many cases. There is a recent study that we have done that we have looked at very worst case scenarios that in close to the equatorial belt where we have significant ionosphere, we see maximum like 40 centimeter. This does not mean that we need only one constant shift to align the entire burst. We have a pixel by pixel offset computed using geometry. Otherwise, we wouldn't be able to do interferometry. The final refinement, based on experience, we have found that a constant shift for Sentinel-1 C-band data has been enough to refine that pixel by pixel offset. So that's the extra, which is constant. I hope that is clear. In some other data sets, that might not be enough. We have shown, France has some many examples as well, that in the past we have realized that you need to account for extra dense offset pixel by pixel or a polynomial in addition to geometry when you are processing L-band over Alaska, because there is a significant ionosphere in L-band over Alaska, or or ever over equator, for example. So there are and the workflows, for example, that are designed for those data, in specifically for what I mentioned, the StreetMap app does that. But for TOPS, it's C-band. We didn't see the we didn't see it to be very, very necessary, actually. After DM registration and DSTLM, okay, so that was a square. And the last one is anyone getting the below text in the output block from the cell just after the heading? What is it? Yeah, maybe your download, Alex, maybe your download was not successful. Make sure you are at the right directory. Usually there is a little bit jumping from this directory to that directory. Make sure you are at the right place to run the cell that you are trying to access the zip file. Either you are at the wrong directory or the data download was not successful. Okay, I hope I have responded to questions. All right. I could quickly show the ASF data download
That's a good idea.
Okay. So usually we had in the previous years, we had the session about downloading data, but yeah, this year we don't have that. There are some materials from previous years, but the problem is the Sasara is not supported. So, but really the ASF Vertex website is very user-friendly and you can explore it yourself. So I assume you all are familiar with this website. You can just use the website to search some data. Let me just choose a polygon. And if it's Sentinel-1, you can limit your search if you want to, for example, the dates that you are interested in. Let's say 2021, March, whatever. And the end date, April 8. The file type, there are many different products that you can play with, but for interferometry, you want the level 1 single log complex data, SLC images. And you can choose that one. The beam mode is the IW. They have different beam modes. And you don't, if you want to make sure that you are, yeah, you can choose which direction the data is acquired from. All right, let's choose ascending. I think that's usually all you need to search, and I'll just push search. Let's see what happens. All right, we already found several. And if I zoom out, our region of interest falls between two tracks, obviously. If you are doing interferometry, you should always make sure that you have the data acquired from the same track, same frame, same path. So you can see that this is path 64, and the other one is 137. So I have clicked on that one. Let me go to my download and delete whatever I have there. All right, so I could just, this one, for example, add it to my cart, and hopefully there is another one. This one also seems to be from the same frame. So I have two now here. You can either download a Python script. If I click on it, it's gonna just download the Python script to my own machine. Then I just really need to run that Python script, just Python 3, wherever that Python script is. Or you could copy the URLs, and in this case, probably that's easier for you since you are on the OpenSAR lab. If you download the URLs, then paste it somewhere, I just paste it here, you have the URLs. So that's all you need really. And you have to use that URL, replace it with what we have in the TOPS app.xml. So in this case, it was XML. Sorry, it was in the reference.xml and secondary.xml. So you have to basically, well, you have to download it first. You have the URL, so we can say wget, let's say this one. Yeah, I have to put in my home.netrc is empty. So I have to put in, if you have that set up, then you just wget that and it should work. The other way that if you want to do the same, and once the data is downloaded, you would just modify the reference.xml and point to the downloaded data. And the other way to make that more, basically do this programmatically, you can just query the, use the API from ASF. They have this very nice instruction on all the parameters that you can search for. Oops, that has changed. All right, but anyways, in the TOPS app, I have two cells at the very top called query ASF and read query. So you can just say query ASF, put in a bounding box and tell it that to put the output in a file like a JSON file and run it, and it will run the query for you. It creates a JSON file that has all the results of the query. And then you can read that file, which is a JSON file, and you can read it into a data frame, a pandas data frame. The URLs are in one column. So I did that, and you have all the URLs. So we really, all we need to do is just to wget those URLs, very similar to what we did in the TOPS app example. So you could do that programmatically as well. So hopefully that's a little bit more clear for the data download.
Yeah, that's good. So on the download subject, this might have been asked earlier, but I was running through the notebook myself, and I just started at the top and worked downward, and that the download script said it couldn't be found, even though it was there. So I was wondering, but the data seemed to be downloaded.
I'm sorry, Paul, can you repeat? I got distracted. I was looking at the message. Was it for me, the question?
Yeah, it was the download script, orbit download script.
Oh, okay.
dloadorbits.py.
Oh yeah, this one.
So when I was just running sequentially through the notebook from the top, everything was working. But when I got to that step, it said that the .py file was not found, even though it exists there.
Oh.
But somehow the orbit directory has the right orbits in it. So I didn't worry about it. I just kept going, but I don't know why that would have happened.
Oh, that's strange. Were you in this cell? I mean, did you run this cell? Because it has an assumption that you are in the orbit directory and you are pointing to.
Certainly, yeah. I just went sequentially through them. It's conceivable that I somehow jumped over that cell by accident. I don't know how I would have, but in any case, it should work. And if it worked for other people, then it was probably something silly I did. I have the orbit.
I think it's you, because it worked fine for me.
Yeah, well, that's not unsurprising. Not surprising. All right, so let's see. We have 10 minutes left. What is the homework for tonight?
So the students are encouraged to, as I said, definitely run this notebook, make sure they can do this, and then run the same notebook and their own data set, TOPS data set over the region of interest. One pair of interferogram.
Okay, I think given the complexity here, just running through this notebook and getting a result may be all that people can do. But yeah, those who are more comfortable can certainly play with more complex things. Are there questions before we end for the day? We have 10 minutes.
Can I ask how people are doing the homeworks for when like reprocessing your own data and stuff? Are you making a new notebook or just doing it on the other end of on the bottom end of the existing notebook, or like will we have trouble with multiply defined variables? I don't know. Is there a convention that's working for people?
That's an excellent question. If you're not familiar with the environment, you can easily get yourself wrapped around the axle. I mean, my recommendation would be to create, the notebook is sort of standalone. And at the top of the notebook, you may remember it basically defines a bunch of subsidiary needed directories below the current working directory where the notebook is. So one solution that I probably would favor myself would be to create a new directory, any place you want, for any given run that you want to experiment with. And then copy the notebook, the IPYNB notebook, into that directory. So that's the current working directory for the current run, and then start modifying the notebook as you wish. Then everything should just end up self-contained in that subdirectory.
You might also want to change the working directory at the top of the notebook.
I think it uses the current working directory, doesn't it? So if you do what I suggested, I think it will do that. Everything will work. But if not, then
well, yeah, maybe that's true.
I mean, the other way to do it is, as Gareth says, you change the top of the notebook to basically point the current working directory to a different place. But that, given there's a lot of relative links and things in this notebook, I think that might be a little riskier than creating a new directory, copying the notebook into it, and working locally.
Sounds good. Thanks for the suggestions.
Does that make sense? You know how to do that, what I was suggesting?
Yeah, no problem. Yeah.
Okay. We have
Sorry.
office hours at 5 o'clock today, Pacific. I think I can be there. And again, 7 a.m. tomorrow morning. So we can answer logistical questions. Haresh, I don't think is available for either of those. So some of the detailed questions on the TOPS processor may have to wait until we can talk to Haresh again, but we'll do our best to answer questions. Usually they're pretty easy, relatively straightforward to answer.
I'll try to look more at. I'll try to look at Slack more often. So.
Yeah, that's the other resource, of course. That's great. Yeah, look at use Slack, and we can get back to you on that.
Gareth, there's a question for you in the chat.
Yeah, I was trying to type an answer to it, but I can say it. How to tell whether something is substance or uplift? You have to. One thing, someone has to tell you what the sign convention is for the interferogram. Is it range change? In which case, blue to yellow to red, from negative to positive, indicates an increase of distance away from the satellite, or is it the other way around? In the ones that we were looking at, and if you process an interferometric pair with the reference image being the earlier date, then it's range change. So negative to positive, blue to yellow to red is an increase in distance away from the satellite. And so if you keep going from fringe to fringe with that sense of color change and that sense of motion, then as you move closer and closer to the source, you're moving further and further away from the satellite, and you should be seeing subsidence or movement away from the satellite in the horizontal direction, potentially. And if it's the other way around, then you have relative motion towards the satellite, and you would be seeing uplift. That's the basic idea. So if you looked at that particular interferogram, if you started at the southwestern end and you followed the profile towards the fault, you saw repeatedly blue, yellow, red, blue, yellow, red, and the ground would have been moving away from the satellite. And if you started at the other end, it went red, yellow, blue towards the fault, which means you're moving towards the satellite, the ground's moving up. Does that make sense?
Yes, that actually does. Thank you. And just making sure. So before, I was just trying to interpret what you're saying is to actually make sense of the interferogram. You need to know if the satellite is going ascending or descending and which direction it's looking as well. So you have to have that information before you look at these interferograms.
Certainly, if it's moving horizontally, that is very important. Yes, and we'll talk a bit more about that tomorrow.
Oh, okay. Okay, thank you.
Very quiet.
Sorry,
There's a
guys.
question about. Oh, go ahead.
No, I'm sorry. I just wondered that is it possible to run this code on our personal device and just upload the results only or the plots instead of using another Python Jupyter or something like that?
In theory, yes, if you're fully installed. I mean, if you have ICE available and you can't run it on your local machine, I guess.
Yeah, I actually tried to install the ISCE software and it worked. So I'm just thinking that why don't give it a shot to try to see everything is fine and just do things together to see what's going on.
Sorry, I have a question related with that. Because I also installed the ISCE from the repository, but when I run the scripts, it tells that maybe some procedures wouldn't work because it required the permission of some proprietary source.
Yeah, that's probably the reason why it does make sense to run it on the OpenSAR lab for now. There's like a million different things that can go wrong if you install ISCE from source. And it's hard to debug unless we can look at your computer directly, and even then it can take a while.
How's that install tutorial coming along?
It's coming along.
I put a
Okay,
PDF
thank you.
for installation via Conda in the Slack channel.
Yeah, I didn't think the Stanford code, which is the proprietary code, was needed for anything that we do, but I'd be surprised if the standard installation required any of that. So is it actually failing, or are you just getting messages that you need proprietary code?
Well, maybe not proprietary code, but it says that some procedures wouldn't work because one required to ask for permission for some procedures. Maybe I can paste the message. Just a second.
I think it's just a standard message when you install the open version of ISCE instead of the full version.
Yeah, I don't think we rely on anything that it's complaining about, so it shouldn't matter for your purposes.
And so toward the end of the week, you will get a Docker container with instructions to deploy it. We don't necessarily want to do that now because otherwise we may get a little bit derailed with the questions for the next few days.
Yeah, Ernesto, I don't think you need to worry about that message for this purpose.
Okay, thank you.
Yeah. All right, well, you have 3 hours to play and come up with your questions for the next round. Okay. Oh, I realized my camera's been off all this time. Sorry about that. All right, we'll talk to you in a few hours, those of you who still have questions, and then maybe again tomorrow morning. If not, we'll see you tomorrow for the lectures. Thanks. Bye-bye.